All right. Hello, everyone. Hope you guys are doing well out there in black screen world. Yeah, so plan for today is to work on worksheet 11, talk about sampling distributions, which we have talked a little bit about already. But I just want to kind of generalize that. We've talked about sampling distributions for means, but I want to just kind of broaden that discussion, talk about sampling distributions for other types of statistics. Any questions before I get started for today about things? Yeah, got homework assignment that was due Monday. Hope that went well. And you've got the next one that is up and due next week. That's going to be our markdown assignment. What we're going to work on today is going to mostly not involve R. So just to kind of recap the bigger discussion, we're working with inference, statistical inference. So the idea is, this is what we do in statistics, is we have some big population. Okay, and usually we don't know like what the population looks like, but we pick one sample over here, and based on this data that we have from this one sample, we would like to make some inference about characteristics of the population. What is the mean, what proportion of the population feels that. So that's where we're moving towards. And we've seen how we can do this already with hypothesis test. And that is we can set up a permutation distribution to then kind of assess the population. But what I want to talk about today is kind of the opposite of what we're going to be doing, which is we're going to assume that we know what the population looks like. And then we're going to pick many samples independently from each other, all the same size. And then we look at the distribution of sample statistics. And which is called sampling distribution. And then once we have an understanding about how we can approximate these sorts of things, then we can think about how, if we only have one sample in that distribution, how could we use that one sample to say something about the population? It is not a simple process. So that's the idea. So that's why we care about sampling distributions, because they're going to be a way for us to make some inference about the population. So in the video, the one that we were thinking about, the distribution that we were thinking about was the distribution of sample proportions, which is called p hat. Yes, and for anyone that grew up in the 90s, that would just be me. Yes, that's like how we used to say things were cool in the 90s. We would say it's fat with a PH. So yes, but we call that a p hat. So the hat means an estimate for the population. And so we can derive formulas for the mean of that distribution. So here p hat, we can think of as saying, if we're thinking about the population being all students, undergrads at, all students at CU Denver, then, then X would denote like the number of students out of that sample who are undergrads, and then we would divide that by N. So that's where the p hat equals X over N comes from. And we could derive these formulas using properties of binomial distributions and properties of expected value and variance. Were there any questions about those results from the video? And hopefully it makes sense that what would we expect the value of p hat to be? Like what would we expect the proportion of students in the sample that are undergrads to be? Most reasonably, we would expect it to be close to what the population is. So if I pick a sample, what is my expected proportion? It's going to be 60%. And here I've got a formula for calculating the variance. And usually when we're working with sampling distributions, instead of using the variance, we describe the spread in terms of the standard error. So for that, we would just take the square root. Yeah, and so the video and there's some files that you can play around with to do these simulations. But the point being here is that these simulations matched what we found theoretically on the previous page, namely that the expected value is getting very, very close to 0.6. So that's what we're observing from the simulations. And if we compare the theoretical variance to what we're getting in these simulations, we see that it's matching up. So what's really important here, which is what we saw with sampling distributions for a mean, is that as p gets large, not p, excuse me, as the sample size n gets large, the expected value doesn't change. It's always going to be 60%. The variance, or we want to describe it in terms of the standard error, right, the standard error gets smaller. We should expect less variation if we pick larger samples. Any questions about that? Yeah, so when we're kind of thinking about different ways that we're going to calculate sampling distributions, we've done a number of these. So we can do exact calculations like we just did here in some cases when we know the distribution of x. We could do permutations like this. So this would be an example of writing out the full sample space. So we've done these types of things already. And then we did simulations when we didn't really worry about whether we generated every single possible permutation resample, but we just generated a bunch of them. So that's what these would fall under. And now we also see that we can use the central limit theorem to approximate the sampling distribution without running a simulation for it. So we've worked with some of these. We'll definitely work with all of them. So I'm kind of going to do this slightly out of order than how these things are in this worksheet, just because these were the questions that you guys did on the reading assignment. So we can kind of start with this. So to kind of just summarize that example with undergraduate students at CU Denver, the sampling distribution for proportion, just like with the means, is going to be normally distributed. We've got the expected value, and now we have a formula for the standard error, which we derived on the first page. So all of this is to say, we need to make sure that our samples are large enough. So for smaller samples, we might not have these properties. In particular, the normal distribution part gets a little bit weaker if we have smaller samples. So we do need to check to make sure our samples are large enough. Once we run that check, then we could say something like the distribution for sample proportions basically those 3 points are just saying it's normal. It's going to be centered at the value of the population proportion, and we can calculate the standard error. So as far as sample size go, right, I don't have the math in front of me, but those are going to check out just fine. But that's what we would want to check. And here, it's not one or the other needs to check out. We need both of those to check out. So this actually winds up being 72, and this is 78. So really what this condition is saying is that in our sample, that we need at least 10 individuals in each group. Okay, here are the groups, meaning like the success group and the failure group. So for us, that would mean we would need at least 10 undergrads and at least 10 grad students in this sample in order to use the central limit theorem. Once we've got that checked, then in this case, what you should have found is the center of the distribution is at the population proportion. So not here, we'll use that later. So from the description up top, we can see that N is 150 and P is 0.48. So this becomes the square root 0.48, 0.52, all over 150. And we take the square root of it. So I'm just going to kind of go through this a little bit quicker just because you guys did think about this, but let me know if you've got any questions about it. So simplifying that, I have some rounding there, but the standard error comes out to about 0.041. So if we want to calculate the z-score in part B, kind of maybe a better way to say this like this. So we're going to take the sample value that we're interested in, which in our case is the 0.4. So to find the z-score, right, usually the calculation is x minus mu over sigma. But now we're not looking at the distribution of individual x values, but our distribution is for p hats. So our value for x is going to be a sample proportion. Our mean is actually the mean of the sampling distribution, which is p. And then we divide by not the standard deviation of the population, but we divide by the standard error of the sampling distribution. So here we've got 0.4 minus 0.48 all over our standard error, which comes out to about minus 1.95, minus 1.96, somewhere in that realm. Any questions? So kind of the picture. If we're looking at the distribution of all of the sample proportions, again, we would expect most of them to be about 0.48, which is the total population or percentage of the population in these 5 cities that speak a language other than English at home. And the fact that we are curious about, well, what about this sample of 0.4, right? Without knowing the standard error, we don't know whether that's close to 0.48 or far away from 0.48. So the standard error is exactly the measurement of saying like, okay, this is the reasonable amount of variation we have in our sample statistics, which is about 0.04. So we can think that we should expect to get samples that have a proportion of about 0.48, like plus or minus 0.04, I should say. So what we can see is that this difference over here is about -2 standard errors away. That's what this z-score is telling us, right? So now we would interpret the z-score not as how many standard deviations away, but how many standard errors away from the center of the sampling distribution is this sample statistic. So that's pretty far away. That's pretty far, 2 standard errors. But finally, if we wanted to calculate this, then we could use now a p-norm function. So I could use p-norm. I just found the z-score. And when I use z-scores, right, then we're using the standard normal distribution. And whatever I get using the standard normal distribution, just keep in mind, we didn't have to find the z-score. We could have just used the sampling distribution and worked with that and used p-norm for that. So remember, with the p-norm function, it tells us the area below, and that's exactly what we would want here. So for those that worked on the quiz, hopefully you all did, your answers might vary depending on how you rounded things off, but it should have been somewhere around here. Okay, any questions about that? So I would just tell you guys, you might want to look back at your old exam 1. There was a normal distribution question. So it was the second to last question on the exam. And the very last part of that problem was a central limit theorem question. And there were some mistakes on that. People using population distribution instead of the sampling distribution to calculate that probability. So, you know, with more work on the central limit theorem, I would definitely encourage you to go back and check out that problem, make sure you did it correctly the first time, and if you didn't, go ahead and try it and fix it. Okay, so let's do another central limit theorem problem for means, and then I'll come back and do the problems in the order that they were on the worksheet. So we're gonna bounce around, but here we're gonna think about central limit theorem for means, and this we already talked about a couple of weeks ago. So in this case, what we're saying is that the distribution for sample means it's not all that different from the central limit theorem for sample proportions, and that is we would expect the sampling distribution to have the same mean as the population. And how do we find the standard errors? We take the standard deviation of the population and divide it by the square root of our sample size. So again, as the sample size gets large, it doesn't affect the center of the distribution. It doesn't have any effect on this, but it does change the standard error. Okay, so the extra thing here is you might be thinking, like, what's the cutoff for sample size, since we had this condition that we needed our samples to be large enough to use the central limit theorem for a proportion. For means, it's much easier to check. We just check to make sure that the sample is bigger than or equal to 30. When the sample is less than 30, we're actually going to use a different distribution to model that. Okay, so in this discussion about, you know, we're picking all of these x's from a population. The sampling distribution is going to be normal no matter how the population is shaped. Okay, so the population doesn't need to be normal in order for the sampling distribution to be normal. What we need is the sample size to be larger than 30. So as the normalness So we might have population where the distribution is heavily skewed, and that's still not going to change the fact that the sampling distribution is going to be normal. So down here, the example I want to take a look at is dealing with a population which is given by a gamma distribution. So a gamma distribution is kind of like a repeated Poisson distribution. So if you remember, when did we use Poisson distributions? This is when we were trying to say, like, if we knew how often things, the average amount of times that things occur in a certain period, then we were able to calculate how likely is it that we get X amount of occurrences in that time period. So with a gamma distribution, we could look at a thing like question 5. So let's say, like, you go fishing and you know that you catch one fish every half hour. So if we wanted to say, like, how likely is it that you catch 2 fish in a half hour or 3 fish in a half hour, that would be a Poisson distribution. But if we want to think about, well, how long is it going to take us to catch 5 fish? So rather than saying, like, how many fish are we going to catch within a certain time period, now we're saying, let's change the time period, and let's think about how long it's going to take for us to catch that many fish. That's where a gamma distribution would be useful. And so for the gamma distribution, there are 2 parameters, one which is called the rate parameter. This is the same parameter that we had from Poisson distributions. So that's what mu is telling us, the mean amount of time between successes, and the shape parameter is how many total number of occurrences are there. Okay, and so X is going to be how much time does it take for us to get that many occurrences. So if we want to think about eventually down here, taking, like, repeated samples from X. And we want to think about, well, what is the mean of those 30 samples? In other words, the sample mean, we'd want to come up with a description for the distribution of sample means. So here it's asking us to approximate what is the probability that X bar is bigger than 3. Okay. Any questions? So in other words, like this, in question 5, we're asked to calculate the mean. I think this means give the mean and not an A there, sorry. Want to give the mean and the variance for the amount of time it takes to catch 5 fish. Okay, and again, what we know is we catch 1 fish every half hour. So we know here that the rate parameter is 5 because we want to know how long is it going to take us to catch 5 fish. And what we also need to know is this rate parameter, lambda. So what would we get for the value of lambda in this example?
How are we doing time in hours?
So this is the mean amount of time. What we want to identify is mu, and then from mu we can get lambda. That's right. And so mu is the mean amount of time between successive occurrences. So it's not saying like, so it's not how many fish are we going to catch in an hour, for example.
Oh, okay. So it's one fish every half hour?
Yeah. Yeah, so if we catch one fish.
I'm confused.
Yeah, so what you're probably not alone. What questions?
So mu is 30 minutes?
Yeah, so mu is going to equal the amount of time between successive occurrences. So this is telling us we catch one fish every half hour. So I catch a fish. That means probably the next fish I'm going to catch is on average taking another 30 minutes, right? And then I catch a fish, and then it's going to take me on average half hour to catch the next one.
Okay.
So maybe let's start with mu, and then we can identify lambda. So what is the mean amount of time between successive fish being caught?
Do the 30 minutes or 0.5 hours?
Yeah, so we'll do this in hours, sure. Since I didn't specify that. You certainly, that's up for you to choose, right? You just want to make sure that you kind of use the right units when you describe your answer in the end. Yeah. So let's say we'll do it in hours.
So then our rate parameter would be 2.
That's right.
That's what I was confused about. I didn't know if we were doing 1/30 or 1/2, how I had it.
Yeah. So actually, either way is okay. Yeah, as long as we're consistent with how we interpret this answer in the end. Yeah. So R is telling us how many occurrences are we waiting for. We want to say 5 fish here. Mu is telling us on average how long do we have to wait between when we catch one fish until we catch another fish. And then lambda is 1 over that time period. So we would say that this distribution has a gamma distribution with parameter, rate parameter, which is equal to 2. I guess first we do the shape, which is 5, and then lambda, which is 2. Not too interested in dealing with like the population here, but thinking about what happens when we pick random samples of 30 out of this population. But point being is that this distribution, this population, is not a normal distribution. It's following a gamma distribution, which is a bit different. So if I want to calculate this probability, we want to be careful that we're using the sampling distribution to calculate this probability, not the distribution of the population. We're interested in distribution of sample statistics. So basically what you can think about is like 30 different people go out to catch fish. They calculate how long it took them to catch 5 fish. And now we're going to calculate what's the probability that the average of those times was longer than 3 minutes. Or sorry, we're dealing with hours, so I should be consistent, longer than 3 hours. So before we calculate this probability, we need to know what the underlying sampling distribution is. We've got a sample which is large enough. So we're going to use the central limit theorem for this calculation. You want to make sure you check that. And again, whether you're looking at a mean or whether you're looking at proportions, that check is going to be different to make sure that the population is large enough. For means, we want to make sure it's at least 30. So what are we going to get for the center of the sampling distribution? So got two options. I want to make sure that you guys are thinking about stuff and doing stuff. I'm not quite sure since I've got black screens. That's cool. Either chat in what the mean is going to be, or if people aren't chatting, I'll take that as you've got some questions, and then maybe we should set up breakout rooms. So I'll set it up so that you can chat me. The question is, what is the value of the mean of the sampling distribution? And then next we'll think about the standard error. Yeah, and so just to kind of summarize some of the results that are coming in, the mean of the sampling distribution, right, is always going to equal the value of the population parameter. In this case,
So in the other sampling that we did, the population was normal. And even though we're working with a population distribution that's not normal, the sample is normal and that rule still applies, that the mean is the same?
yeah, so the central limit theorem, all of this stuff is true no matter what the population looks like.
Okay.
So if the population is normal, if the population is gamma, if the population is exponential, if the population is something that we don't even know what it looks like in theory, the underlying sampling distribution will be normal as long as the samples are large, the size of the samples is large enough. So these properties, 1, 2, and 3 are more and more accurate. It more depends on the size of the sample than really the shape of the underlying distribution. The larger our samples get, the better, the more accurate these statements become. So yes, I was getting some specific answers, and some people were chatting in things a little more general, like the sample mean is going to equal the population mean, that's definitely the case over here. The question is, what is the population mean? And for that, people were, checking out that, okay, we've got a formula for the expected value for gamma distributions, and it's the ratio of these two parameters. So I would take the shape parameter, which is the 5 fish, and then I divide that by lambda. And here lambda is 2. So you would expect, if you to catch 2.5 fish, excuse me, you would expect to take 2.5 hours to catch 5 fish. That's what this is saying. So that's how we could interpret that value. It takes on average 2.5, that's a decimal point in there, 2.5 hours to catch 5 fish. That makes sense if it takes about a half hour in between catching fish, right? So that's why we are simply just really taking 5 fish times half an hour per fish. That gives me 2.5 hours. So if you have questions, please, feel free to say them or chat them in. I've got a chat open too. But it's really helpful. Thanks for your replies. It's good to see what you guys are thinking. Any questions about this part of the puzzle? I think both how we calculated it and like what is it actually telling us. What we're thinking about is times that it takes to catch 5 fish. And so on average, we see it takes 2.5 hours. Okay, so then next would be the standard error. The standard error, in general, the formula is we calculate the standard deviation of the population and divide by the square root of n, right? And that's equivalent to saying we could calculate the variance, divide by n, and take the square root of that too. So depending on whether you're given the standard deviation of the population or maybe the variance of the population, you could use either of those. So we've got a formula for the variance over here for gamma distributions. So again, go ahead and give it your best shot to calculate what you think the standard error would be for this case and chat it in to me when you think you've got it. Okay, so getting mostly consistent answers here. I'm not sure if there's some, I think there's a lot of things to type here, so I think there might be some typing errors here, but right, so what we would do is we would take the variance, we can calculate that first, which would be the rate, which is 5 over 4, right? We take lambda squared. So the variance of the population is 5/4. So in other words, the standard deviation is the square root of 5 over 2. That's the standard deviation for the population. So then to calculate the standard error, we would take that standard deviation, which is square root of 5 over 2, and divide it by the square root of our sample size, which is 30. And based on the chats that I'm getting in, people might be varying with their estimates a little bit, but it looks like it's like 0.2282. Okay, and so again, we are getting that value from this formula for the standard error, which in general is find the standard deviation of the population, which we did over here, found the variance, took the square root of the variance, and then we have an additional step where we now need to scale that down. We divide that by the square root of the sample size. So that's where this square root of 30 comes from, is because the sample size was 30. So now we have a distribution, not for the population, but if 30 different people went out fishing and they all came back and said, this is how long it took me to catch 5 fish, we have a distribution for what we would expect the average of those times to be. So if we wanted to calculate what is the probability that X bar is bigger than 3, knowing what we know here now about the distribution for X bars, I'd like you guys to chat me in. What's a formula that we could use in R to calculate this, now that we know the distribution for the sample statistics? So in other words, this should be some form of a p-norm function. Okay, great. These were coming in fast. Very good. Yeah, and they all look good. I'll just say you want to be careful that the p-norm function gives you the area below 3. And so if you want to get the area above 3, you would just use that p-norm function and then just subtract it from 1. So over here, we would have like p-norm. We first plug in 3. That comes from over here. That's right. And then we plug in the mean, which was 5 hats. And then the standard error, not the standard deviation, but the standard error, which was this. Okay, any questions about that? So, again, the important thing here is we would have done this process the same exact way, no matter what the population looked like. The only thing that would change would be like how we find the mean and the variance for the population. That depends on what the distribution X is. But once we find these values, the sampling distribution will be normal. Any questions? Yeah, and so if you're kind of curious about playing around with gamma distribution, feel free to kind of do this similar sort of simulations that we did with the distribution for proportion. You can probably play around with trying to tweak this code to do a similar simulation to see what happens to sampling distribution for a gamma distribution when we change the sample size. But I'll just leave that for you to play around with. Okay. So that's been focusing on, we've been talking about these different ways. This would be, those last couple problems would fall into that boat where we're using the central limit theorem to calculate the probability that X bar is bigger than 3, as opposed to telling R to create a whole bunch of simulations for us and then estimate that from the simulations. But we've done that too. Okay, so we've been talking about sampling distributions for X bar and for P hat. Some other sampling distributions that we'll think about are differences in two sample means if we have two different populations, and differences of sample proportions. We've been doing simulations of these things with permutation resamples. And also frequently of interest are things like, what's the minimum value of my data set? What's the maximum value? What's the probability that the smallest value in my data set is going to be less than this? What's the probability that my largest value in my data set is going to be more than that? So other interesting sample statistics that we might look at are max and min in addition to mean. So here, let's try and find a general formula for how we can do the maximum value. So here, there's going to really be no mention at all of what the distribution of individual x values is. We don't know anything about x. But you know, I can go out and take a random sample of, you know, housing costs for 100 houses, and then I might ask, what's the probability that the maximum value in my sample is more than $1 million or something like that. So so capital F of x is denoting the cumulative distribution function for x. Maybe I'll write it like this to pick a different letter. So for example, if I wanted to know what's the probability that x is less than or equal to a, right, I could use the cumulative distribution function to calculate that for me. So now we take a sample of n different things from population x. And then we look at all of these things in our sample, and we want to ask, like, you know, what's the probability that our maximum value is less than or equal to a? So that's consistent to saying, like, what's the probability that every single value in my sample is less than or equal to a, right? Since if any one of them was bigger than a, then our maximum value wouldn't be a. So any thoughts about what we can do to try and calculate this probability? This is all very abstract. We actually don't have a value for a. We don't know what x looks like. But what I would like to do in order to calculate what is the probability that the maximum value of x in my sample is less than a. So that means, what's the probability that the first one is less than a, the second one is less than a, et cetera, et cetera, et cetera. So any thoughts what we can do to try and simplify this? If I have two different random variables, probability, say x and y, and I'm going to assume that these random variables are independent. And I want to calculate the probability that x is less than 3 and y is less than 3. What's special about the fact that they're independent random variables that would allow me a nice way to calculate these probabilities? Yeah, I don't think I'm just getting some suggestions in here. We don't need to do anything about sequences, or series, or things like this. We don't have a sequence of X values. In fact, like what we have is each X value observation is independent of the other one. So we're pulling these values of X all from the same population, but we're pulling them independent from each other. That's right. And so I'm seeing some responses here that when random variables are independent, then that means the probability that A occurs and B occurs is equal to the probability of A times the probability of B. So we don't want to forget all of the work we did last month. These things are going to be independent, then we have this multiplicative rule. And if they're not independent, then we have to be more careful. But for us, we're told that each of these observations is independently picked from the population. So the likelihood that the first value is less than A is independent of the odds that the second value is less than A. That's independent from the odds that the third value is less than A, and so on. So all of these observations are independent from each other. So we are trying to calculate the cumulative distribution function for this statistic X max. And all I know sorry about that. And what we're going to use is the fact that we're going to let F denote the probability, the cumulative distribution. So in other words, the probability that X is less than or equal to A. And what I'd like to do is find a corresponding function for the cumulative distribution for X max. And so in order for the maximum value to be less than, to equal A, I should say, that would mean that every single one of these values has to be less than or equal to A. Right? Otherwise, A wouldn't be the maximum value of that sample. So really what we want to say is probability that each of these things, each of these individual observations is less than or equal to A. And because these are all independent observations, we can break that up. Okay, since these are all independent observations. then I can calculate each of these values. So the probability that any one of these observations is less than or equal to A, what's a function that I could use to calculate this?
That's just a p-norm since we're working with the sample distribution.
So here the population, we don't know if it's normal or not. And the sampling distribution for means and proportions are normal. We don't know that that's the case for this other statistic, which is the max statistic. So far, the only sampling distributions that we have theoretical ways to construct are for a mean and for a proportion. We actually don't have a theoretical description for the max, but that's what we're going to try and come up with. So I'm not looking for a number or a value or something I would enter into R, since we're dealing with things a little bit more abstractly at the moment. But if I want to know what is the probability that X is less than or equal to A, right? Don't we have a formula for that already? That's what the cumulative distribution function is, right? Each of these X's is a separate observation picked from this same population. So the odds that this first number that I picked are being less than or equal to A, I would use the cumulative distribution function for X, for random variable X, whatever that is. And since we're picking all of these values from the same distribution, they all have the same cumulative distribution function. So in other words, it's equal to the cumulative distribution function evaluated at A raised to the nth power, because we have n of these observations, each one is independent. So we can just multiply those n probabilities together. So it's really important that you guys ask questions when you're not certain about something, because you will have to do something more difficult on homework. So this is the time to ask if you've got questions, or office hours, of course. But we're all here. We're on Zoom. So now's the time to get some immediate feedback if you've got some questions. Okay, so that's great. Let's set up 2 breakout rooms then to work on question 4, which will practice this concept. So we'll see if we've got some questions. One room will go with Yua, one room I'll sit in on, but I think it's good for you guys to have some time to talk to your classmates about this. So when you go into the rooms, if you're someplace where you can't turn your camera on, that's fine, but turn your microphone on, say hi to your group mates, make sure they know you're there, and you and I will try and make sure that you guys are staying on course. But what we're going to be working on is question number 4, parts A and B for that one. Okay, so rooms are opened up, and you and I will kind of be checking in on you guys. Idea here is for uniform distribution, right? These are distributions where f of x is constant, right? When we're talking about the PDF at least. And so if we're told that the domain here is going from 0 to 1, really what we need to do is figure out like what's the height of the function. So trying to write with the mouse here, but the PDF is going to be 0 for any values outside of 0 to 1. And between 0 and 1, what's going to be the value that we have over here?
1.
How'd you get that?
1 over b minus a. So
Yeah.
1 minus 0 is 1. 1 over
Sure.
1 is 1.
So one way to think about it is we have a shortcut for the PDF for uniform distributions. Another way to think about it would be, right, it's going to have to be the value so that the area here is equal to 1 as well. So if you forget that formula, at least we've got this general idea that the total area underneath the PDF should be 1. And if the width is 1 and this is a rectangle, well, then the height is 1 as well.
So then the CDF would be 0 if x is less than 0, x if x is between 0 and 1, inclusive, and then 1 if x is greater than 1.
Let me see. So you said it's going to be 0 if x is less than 0. For 0 to 1, you said it was
Just x.
just x, and then it would be 1 over here. So how did you get that x?
The shortcut is x minus a over b minus a. A is 0, b is 1, so it's just x.
Okay, yeah, so there's a shortcut that says it's x over b minus a, where for us, here's our value for b, here's our value for a. And in general, it's kind of good to just review, like if we know the PDF, what's the operation to get the CDF?
Just integrate.
Yeah, that's right. So we would integrate this to get that as well. And that is consistent that when we integrate 1, we get x. Good. And so what we just kind of talked about from the previous problem was now we have a formula, right? No matter what the cumulative distribution, no matter what f looks like, whether it's uniform or anything else, we know that the max function looks like this. So I can use some information about the CDF of x to get some information about the CDF for x max. And so this problem is saying, okay, we're going to pick a sample size of 10 things out of the uniform distribution. And we want to calculate what is the probability that x max, it's really hard to write with the mouse, is greater than or equal to 0.9. Keep in mind, this function that we have over here is the PDF for x max. So this would tell me the probability that x max is less than or equal to a. Right, since cumulative distributions tell me area to the left. So I need to be careful about how I adjust this, because this is asking me to calculate the probability that not that it's less than 0.9, but that it's bigger than 0.9. So kind of this part over here, we found in the previous example, and this is what it's asking us to think about now. And part of that process is going to be, well, we have a formula for the CDF of x. So any thoughts about what we could do? Do you mind explaining what you were doing? What, was it Hannah?
I'm not sure too.
Okay.
I think for a CDF that bigger than 0.9, it would be 1 minus the CDF that less than 0.9.
Okay. Yes.
So
That seems like a step in the right direction. That okay. This is asking me to calculate the probability that it's bigger than 0.9. However, the formula that we talked about in the previous problem is useful to calculate the probability that x max is less than or equal to something. So let's calculate the complement of that, which in other words says, let's calculate the probability that the maximum value is less than 0.9 and then subtract that from 1.
Yeah, exactly. And
So-
if x less than 0.9 will be x, right?
Yeah, so we've got a formula for this one over here. That's right. So just to kind of fill in the detail, right? What we're going to calculate is the probability that x max is less than 0.9 and subtract that from 1. And that's going to be equivalent to since these two probabilities we need to add up to 1. Either x max is less than 0.9 or it's greater than or equal to 0.9. And then the probability that x max is less than 0.9, that's exactly what we use the CDF function to tell us. So here we can plug in 0.9. So kind of what the logic here is, well, first, this is really nothing to do with sampling distributions or uniform distribution. We're first just kind of using this property of complement events. And now we need to use all of this stuff that we just developed in the previous parts. So from the previous example, we learned that this is going to equal the value of f of x evaluated at 0.9. Hope you guys are dealing with my writing here. And then we're going to raise this all to the power of 10, since that was our sample size. So all of this stuff right here, I'm using for this right here. And we know that formula from the previous problem that we have over here. So now we've got 1 minus, and then the last thing to do would just be evaluate our CDF at that point, 0.9. Yeah, and I don't know if someone has a calculator handy, what this comes out to be.
0.6513.
Yeah, that's what I get to. So this, yeah, so this becomes like 1 minus like 0.3487, which is equal to, I don't know why I can't just type this out now, would be 0.6513. Okay, any questions?
I have this question. Why we don't use 1 minus the CDF first and take 10 like the square of 10? Sorry,
You know, I
forgot.
understand what you're saying. Yes, that's a really good question. But let me answer that with everybody. I realize there's another room and we're gonna leave in a minute. So good question, Hannah. I'm just gonna bring us back into the main room and we can talk about it there. And the question was, is this equivalent to saying this? So like mathematically, right, those are not the same statements. Is the first thing to kind of just keep track of. So these two are not equal, but to kind of see the theory about why that might be true. So each one of these things individually is really like saying 1 minus the probability that x is less than 0.9. So in other words, each of these things is telling us what is the probability that any one value of x is bigger than 0.9. So I think the problem there is you might be thinking about this as saying, what is the probability that x1 is bigger than 0.9 and x2 is bigger than 0.9 and so on. And what we want to see is we want x max to be not bigger than 0.9. So I see. So that's different than saying we want all of these things to be bigger than 0.9, right? If I have a data set that looked like we're picking from a uniform distribution from 0 to 1. So maybe I have this, I have another entry like this. So the fact that if I picked a sample like this, this would satisfy the fact that x max is bigger than 0.9, right? But that doesn't require each individual thing being bigger than 0.9. So when you calculate this probability over here, this is saying what's the probability that all of these are bigger than 0.9. So that's what this is calculating over here, which is not what this problem is asking. It's saying, okay, what's the probability that we need like one of them at, is bigger than 0.9. I don't know if that answers the question, Hannah. Good, thanks. Okay, so that was all. I just wanted to handle that one there. But if anybody else has questions, happy to stick around. I've got office hours tomorrow to chat about any homework problems that you might be working on. Otherwise, you and I are here to help, so don't be afraid to reach out to us if you've got questions. Otherwise, have a nice weekend, and I'll see you guys on Monday.